Yeah, welcome to our next session here in the Chrysler Pavilion, where we will focus now within the sea ice day session here on Antarctic sea ice and its current status and what is actually also the consequence, not only on a local scale, but also in particular on a global scale in relation to climate change. And therefore, I'm really happy that I have a nice list of panelists here that join me for this today's session. So my name is Stephanie Arndt. I'm a sea ice physicist at the Alfred Wegener Institute for Polar and Marine Research in Germany, and I'm also affiliated with the University of Hamburg, holding there my professorship. In addition, we have then online from Tasmania, from Australia, Will Hobbs, who is also a sea ice physicist, however, is more looking into models and model applications. We have then here on stage Robbie Mallet from the Arctic University of Norway, also looking into sea ice physics, both from the observational point of view, but also again into the interaction with the whole climate system. We have then here also on stage Jacqueline Steffels from the University of Groningen in the Netherlands. She is a sea ice ecologist actually, and that's really nicely connecting the sea ice physics to the sea ice ecosystem. And last but not least, we have also from Australia, Petra Heil from the Antarctic Australian division, who is there also working on the sea ice physics, but also looking beyond the pure physical point of view, but also in relation to politics. And this is actually also what we will now dive into within this session here. So we will start looking into the general status of the Antarctic sea ice, and which will be then followed by discussions on what are potential drivers bringing us to the current situation that we are facing in Antarctica. However, as I said, it's not only about the local effects, but it's in particular about the global effects, which Robbie will then dive into, and afterwards we will then look into the ecosystem and the consequences for the ecosystem of the in relation to the Antarctic sea ice change, and then last but not least, also look into political implications. So what is actually needed to be done, just like on really again the global scale, also in relation here to the COP conference. And with that, I will start looking into the actual Antarctic sea ice observations and trends. So what are we actually talking about? So when we talk about the Antarctic sea ice area, in contrast to what we observe in the Arctic, in the Southern Ocean, we have in the central part sitting the Antarctic continent, which is actually surrounded by the Antarctic sea ice cover. And this is actually also like kind of shaping how the sea ice is developing in the season, as you can see here now on the right hand side animation, where we can see that the sea ice can spread really, really far across the Southern Ocean, given that the whole sea ice extent is mainly wind-driven. This causes in the end that we push the ice constantly off the Antarctic continent, which is then allowing for more and more sea ice production, which by the same time as sea ice forms, most of the brine of the salt of the Southern Ocean is not incorporated into the ice structure. Most of it is just like released to the upper ocean, sinking down to deep oceans, where it's forming our really global important Antarctic bottom water masses, which in the end drive our whole global ocean circulation system. However, when we now look into the evolution of the Antarctic sea ice extent over the last decades, until let's say 2015-16 roundabout, we had a rather constant sea ice extent in summertime. We even talked until the last IPCC report about a slightly increase in the sea ice extent, as you can see it here. Now, given the anomalies, so how did the Antarctic sea ice change in relation to the overall average? So looking onto that, we always were wondering, well, our models do predict already since quite a while that we should observe a strong decrease. However, we haven't done. And we were largely discussing where this is coming from, as we had still given our limited observations, we had still no real clue how this is fitting between observations and the forecast. However, since now 2015-16, we are kind of, it seems like at least, that we are kind of in a phase now where this changed dramatically. So now over the last 7 to 8 years, we have constantly negative anomalies, in particular in wintertime, as we will just see in a moment. And this, just like this evolution, gives us evidence that obviously the Antarctic sea ice regime has also changed, most likely in a similar way as it does in the Arctic, so which will have also like huge global implications, as we will see later. Zooming in here a little bit more to the seasons, you can see here now again the anomalies in the Antarctic sea ice extent shown for the different seasons. So the gray lines show all the years, like from 1979 to 2022, whereas then we had this, in particular, drastic change in 23 and 24, so the last two seasons, where we see in particular during the winter time this drastic decrease in sea ice extent. And this decrease is not only observed like in parts of the Antarctic region, but all over the place, as you can see on the right side image, so that it's like really a global topic when talking about the Antarctic sea ice change. And with that, I hand over to Will Hobbs in Australia, giving us insights into the actual potential drivers of these Antarctic change.
Thank you, Steffi. Just checking you can hear me.
Yes, we can.
Right, so as Steffi said, I'm Dr. Will Hobbs, a sea ice researcher at the Australian Antarctic Program Partnership, and I'm speaking to you from Nipaluna, Hobart in Australia. I just want to give a very brief overview of the physical processes that drive sea ice variability, and in particular, which ones are important for the recent years. Now, of course, the most important and pressing question is whether these recent events are anthropogenic and what that means for the near future. And to do that, we need to consider both observations and climate models. Steffi, could you move forward, please? So this rather complicated figure actually shows output from Access ESM, which is Australia's Earth system model, and it shows how Antarctic sea ice extent reduces with global surface air temperature. Each of those grey lines is one of 40 different model runs. So the spread between them indicates the variability in the system. And so you can very clearly see that as the planet warms, the sea ice decreases. And you can see the red dots, which show the observed state over the last 45 years, do the same thing. Recent losses coincide with some of the warmest years on our planetary record. If we look closer, you can see that those red dots, the observations, do fluctuate a little bit more than the model's representation, which indicates that the model somehow misses some of the process, some of the natural variability, even though Access is actually considered one of the best representations of the Southern Ocean and Antarctic climate amongst the models that are used, for example, by the IPCC. So to bolster our confidence in the models and what they're telling us about the future, we actually need to think a bit more about the physical process, the actual drivers of these recent changes. So Steffi, if we can move to the next slide. So Steffi's already said that the biggest driver of variability is the wind, and that's certainly been the case until recently. And this is demonstrated. So the winds here are shown by the arrows, and sea ice gain is shown by blue shading and loss by red. And you can see that if the winds are moving from the north towards the continent, they push the ice up against the continent and they bring in warm air, which results in less sea ice. The opposite is true when the winds come from the continent. They push the ice outwards, they bring in cold air and get more melt. So that really strong coupling, is there a technical problem? We good? Can somebody confirm that you can hear me?
I can hear you.
Is there anything?
Okay. Can you hear us now, Will?
I can hear you just fine. Can you hear me?
Perfect. We can also hear you as well. So you got just interrupted when you explained the importance of the wind.
Okay. Right. Well, I'll just briefly say, yes, that the winds are incredibly important. And the winds really explain, or the atmosphere explains, most of the sea ice variability that we've observed since our satellite records began in the late 70s. But that's not quite the case anymore. And if we can go to our next slide, I've got another demonstration. So this is output again from a model. This is an ocean sea ice model. So it's been given information about the real atmosphere. So the model output sea ice area is shown by the colored lines, the red and the blue, and the observations are in black. And you can see that the model tracks the observations incredibly well, even though it only knows about the atmosphere. And that really strongly demonstrates that role of the atmosphere. But if we look closer, we can see that the model doesn't quite capture those big drops in recent years. And in fact, the model produces sea ice that's a little higher than observed. And it's a little clearer if we focus on the bias. Next slide, please.
I can't click anymore.
There we go. So this is the bias, which is the difference between the model and the observations. And you can see how that bias ramps up after 2016. The models represent too much sea ice. Now, this is a fairly simple demonstration from just one model, but is part of a whole raft of evidence from both models and observations that the atmosphere alone cannot explain these recent changes. We have to look to the ocean. Next slide, please. So in recent years, the Southern Ocean sea surface temperature, shown by this time plot, has been unprecedentedly warm. And we know that that seems to be having a big effect on the sea ice. But the big question for the scientists now is where that heat is coming from, because that question is really critical to understanding whether this is an anthropogenic event and what our future looks like. So if we go to the next slide. So the first thing to know about sea ice is that it's a really good reflector of sunlight. And so if you have a summer with low sea ice cover, the ocean is able to absorb more sunlight and warm up, and that gives you less sea ice the next year. We call this the albedo effect. Now, because we've had multiple summers with very low sea ice, it could just be that the ocean is absorbing more heat at the surface, and this is a long-term sustained response to, for example, a natural event in 2016. We can't rule that out. Next slide, please. Now, this figure is actually showing Southern Ocean temperatures, but this time in depth, averaged over the Southern Ocean, over depth and time. And you can see that, again, at the surface, if we look after 2016, near the top of that figure, that big warming that we already saw on that previous slide. But you can also see that the deeper ocean was warming below the mixed layer as early as 2012. Now, it was previously thought that that deep ocean protected the Antarctic sea ice from the worst effects of climate change. But we now know that that deep ocean water mass actually has a robust anthropogenic signal. So if it is water from the deep rising to change the sea ice, that probably implies an anthropogenic signal, and we could be in for a long-term sea ice loss. Next slide, please. Oh, click again. There we go. And finally, we've also noticed that mid-latitude sea surface temperatures in the Southern Ocean have been really warm lately. And it's possible that that heat is crossing the Antarctic circumpolar current, which is a really complicated current that separates the polar waters of the Southern Ocean from the rest of the ocean. Is that heat crossing? That's another possibility for what's driving these events. Finally, I'd like to summarize there with the next slide. So the main message is that we know the ocean has been really, really important for these recent sea ice losses. But there's multiple plausible sources of this ocean heat. And whether this is an anthropogenic signal that's likely to continue for the long term, or whether this is just some strange piece of internal variability that we've never before observed, really comes down to where that heat is coming from. Thank you.
Thank you, Will. And with that, I hand over to Robbie, actually, here on site, to talk about the impacts on a global scale.
Thanks. I'm going to talk about what are the impacts of these changes now that Will's described the potential drivers. And I've taken a kind of loose interpretation of climate here. So I'm going to touch on three things. One is this albedo feedback that we've seen. The other one is changes to the degree of protection that ice sheets and ice shelves and marine terminating glaciers will feel from sea ice retreat. And the third is going to be what I think is maybe the most alarming is potential changes to the Southern Ocean carbon sink. So that is the ability of the Southern Ocean to remove carbon dioxide and other things from the atmosphere. The authors evaluated the change in the radiative effect of sea ice over the last few decades. And they call it the sea ice radiative effect rather than just the albedo, because sea ice retreat is actually a kind of complex thing. So we talk a lot about how fresh snow on sea ice can reflect maybe up to 90% of the incoming sunlight, whereas the ocean below can absorb up to 90%, and sometimes. When the sea ice retreats, we also see a slow increase in the cloud cover. And there's a potential that that's buffering the effect of sea ice retreat on the total albedo of the surface. But finally, there's also this effect where the clouds that come in, they also trap outgoing heat radiation, long wave radiation, and they potentially warm it up. So clouds have a very complex role, and the fact that clouds are changing at the same time as the sea ice can really make things difficult for as a scientist to work out what the effect of sea ice decline is. But people are now starting to do the maths, do the physics on this with multiple different data sets. And the results are clear, and they're also consistent with the simplest explanation that sea ice retreat results in warming. So here is a map of the increase in red and the decrease in blue of the radiative forcing at the top of the atmosphere from all of these three effects. So sea ice albedo, cloud trapping of long wave radiation. And it turns out that in recent years, this is a comparison of post 2016 to the 1980s, we've seen widespread large increases in the radiative forcing of the surface from these sea ice declines. So and when expressed as a time series on the right-hand side of the plot, the sea ice radiative effect, SIRE, we see a real jump no matter what data set you use in this radiative effect. So all the different lines are basically different permutations of cloud data sets, satellites, different ingredients you can use in this recipe. But no matter what recipe you use, it tastes the same. The radiative effect has increased in response to sea ice decline in recent years. I just wanted to show another map before moving on to the next section. So this is a typical distribution of winter Antarctic sea ice. And you can see it acts as a protective halo around the continent of Antarctica. Antarctica is quite distinct from the Arctic in the sense that it is an island covered in ice surrounded by ocean, whereas in the Arctic, it's very much an ocean surrounded by land. So the sea ice in winter provides this buffering protective halo around the continent. And it potentially has profound protective effects on the ice where that ice terminates in the ocean. Here's a photo I took last year of my colleague against some of this ice that terminates in the ocean. This is a Rothera research station in the UK, and we're on the sea ice here, skiing around. And you can imagine if that sea ice weren't there, those waves are going to be lapping right at the foot of that glacier. The waves of salty, potentially quite warm ocean water, which can provide quite a detrimental effect on ice that's accumulated over many, many years. So the ocean is really connected to the Antarctic ice sheets and ice shelves in an immediate way. Here's a video that I took the year before from Polarstern near Steffi's National Research Station of Neumayer in Antarctica. And you can actually see the swell there penetrating through the sea ice pack to hit the ice shelf just beyond. That's not a marine terminating glacier like in the last slide. That's an actual floating ice shelf. And hopefully you can see even from this short and kind of bad GIF that I've I've made, that the swell does actually make it. This isn't the wash from the ship. This is ocean waves coming in through the marginal ice zone and affecting those ice shelves. So this is a real service, a system service that the sea ice is providing to the continent of Antarctica. There's research on this, as well as my anecdotal photos and videos, be assured. So we've actually seen the breakup of quite large ice sheets like Larsen A and Larsen B on the Antarctic Peninsula, and also the Wilkes ice shelf in response to sea ice breakout and retreat. So here's a picture of that Larsen B ice shelf a month apart, before and after this pretty catastrophic collapse documented by the paper above. And there's robust evidence that was driven by ocean swell penetrating through areas that are no longer protected by sea ice. Just finally, the last item on my short agenda is the role that the Southern Ocean plays in sinking carbon from the atmosphere. So carbon dioxide, as we pump it into the atmosphere above, is absorbed by the surface ocean below. And then in certain parts of the world, we're able to, well, not we, but the ocean is able to sink this carbon-rich water to depth. One mechanism here is the formation of Antarctic bottom water, which is a very salty, very dense cold water mass that's produced by on the shelf seas around Antarctica, and then fills what we call the global abyssal plain, which is this very deep bottom level of the ocean, where we can basically sequester large amounts of carbon at the surface, and that provides another system service. But this Antarctic bottom water is critically dependent on sea ice. So when the sea ice retreats, we lose our ability to form this carbon-rich water and sink it safely to depth. And we're talking about water that's stored for literally thousands of years here. So this is a major and long-term perturbation to the system. As you might expect, it's not just my observation. So there's a lot of research coming out, particularly in the last 2 years, actually. So these top two studies, they're observational studies and studies on the present. And the bottom study is a modeling study that I think had some really powerful findings on the future of the Weddell Sea and the way that we form dense water there and sink it down into the deep ocean, where in many respects to humans it's safely sequestered. I think of it kind of like a nuclear storage bunker, right? When we make this nuclear waste, we have to build these enormously expensive billion-dollar facilities to store this stuff. But in the sense of carbon, anthropogenic carbon, the ocean does this service for us. So I think it's really, really valuable. And this last point about the carbon storage is particularly the one that keeps me awake at night, because we're not just messing around on the scales of our own lifetimes, but they're the lifetimes of our children and many, many generations to come. So hopefully I've convinced you, using these three examples of the sea ice radiative effect, the protective halo around the ice sheets and ice shelves, and their ability to sink carbon, that sea ice decline is something to be really worried about in terms of the broader Antarctic system. So now I'm going to hand over to Jacqueline, who's going to talk about the biological impacts of this sea ice decline.
Thank you, Robbie, and thank you all for organizing this meeting. I have the honor to speak to you about the ecosystem. That's a part that has not been mentioned that often. So I will try to guide you through the impact of climate change on the Antarctic ecosystem. So sometimes pictures say more than words. This is a specific picture of the globe, showing how incredibly important the cryosphere is. And if we compare that to other biomes and habitats on the terrestrial system, then the Antarctic sea ice zone is 18 million square kilometers, which is comparable to all rainforests together. And in my last slide, I'll come back to that. So sea ice in Antarctica is quite different from sea ice in the Arctic. It is incredibly rich. It's of unicellular algae that thrive at the underside mainly of the sea ice, but also within the sea ice. And these algae that they form the bottom of a very, very rich ecosystem. That they basically form such a luxury dinner for grazers like krill that you see on the picture in the middle. And that has other implications for higher trophic levels for the predators that also feed on the krill, like penguins, seals, but of course also the greater whales. So this is the ecosystem, but it's not only the ecosystem that sea ice is important for, it's also the so-called biogeochemical cycles that are important. That is a kind of an overarching study to see how the biology and the chemistry involves in the cycling of climate relevant cycles like the carbon cycle. We all know that, but there's also other compounds that are very important for climate regulation. One of those things is the source dimethyl sulfide. You see it on the left of the figure, and that is a very important source for clouds. So it is understanding the system, the sea ice system, and the role biology plays in that is instrumental to understanding how sea ice ecosystems contribute to the drawdown of CO2 and the production of this DMS, of both these climate relevant compounds. So now I'll guide you through how this is currently going to change. So one of the main sites where the Antarctic ecosystem has been studied is the West Antarctic Peninsula. Since 1992, the Americans have studied that together with a lot of international collaborators, and what we see is a change over there. Normally, we have a polar system, which means that there is a lot of sea ice covering the ocean underneath. And that means that winds and weather cannot penetrate very deep because it's basically capped by the sea ice. And that means that underneath the sea ice, there is a very rich ecosystem going on. And it has a short food chain, so the algae that are formed at the underside of the ecosystem goes straight into krill, and being a key species of in the ecosystem, it goes directly to the higher trophic levels like whales and penguins, etc. It also results in the drawdown of CO2 through the so-called biological pump, which is different from the one that Robbie just talked about, that is the physical pump, but the biological pump has the option of really storing CO2 in the sediments. Basically, what we are producing, what we are currently using up, the fossil fuels, that's the remnants of these guys. How are we going to change? If there's less sea ice, that means more wind can penetrate into the ocean. That means that there's more mixing going on. And that also means that the whole ecosystem will change. There will be longer food chains. There will be more remineralization, less quality of food will be produced for the higher trophic levels. And that also means that there's less CO2 will be taken up from the atmosphere and exported to the deeper ocean. So this has tremendous implications for the whole system. Now, this change in food chain will have implications on higher trophic levels. There is a cascade going on, which means that organisms that benefit from sea ice, that are actually have life cycles that need the existence of sea ice being there, will be replaced by organisms like salps on the lower panel that are, well, you can already see it. This jellyfish is not very attractive for whales, whereas the krill, they are the main source of a very rich dinner. So change shifts which have already occurred around the Antarctic Peninsula will have a cascading effect on the higher trophic levels that we should not underestimate. And we actually already see this happening. It's not only the food source for the higher, for this iconic organisms like the emperor penguin that is going to be diminished. Also, the early breakup of sea ice will result in a catastrophic failure of breeding. And this actually happened in 22, quite close in the Bellinghausen Sea, quite close to the West Antarctic Peninsula. If we're going to continue like this, everybody, all the models actually predicted by the end of this century there will be no emperor penguin left. Which, well, I mean, you can be ironic about it, and why would we care about emperor penguins? But, right, I mean, they are incredibly beautiful and very important for the whole ecosystem of the Antarctic. So, coming back to the biogeochemical part of the thing, changing the winds when there's less ice on the water will increase the so-called mixed layer that will have an impact on the exchange of CO2 and DMS and other climate relevant process gases that have an impact on climate, like cloud formation and the albedo of the skies. But basically, if you look at all the white question marks, we hardly know how the feedback mechanisms will work. So we know that there will be huge differences going on, but how it will feed back on climate regulation is largely unknown. So take home message, as I promised you, the shift in the whole ecosystem, when the sea ice disappears, this is comparable to the change in to the diversity we are going to that is currently under threat in coral reefs and all the tropical forests. We are very concerned about it. Maybe the whole of COP and especially the COP on biodiversity is very worried about tropical forests. But we are facing the same extinction when we lose our sea ice. And nobody cares about it, but we should care about that. So it has cascading impact on the whole ecosystem, and what we know about feedback, climate feedback, is largely unknown. So I can only reiterate: it's no option to wait. We are seeing things happening, as Robbie already said. We cannot afford to have the temperature increase above 1.5. And with this, I want to add on to Petra, who will talk about future priorities.
Yes, thank you, Jacqueline. Can you hear me all right in the room?
Yes, we can.
Okay, thank you. So thank you for the opportunity to speak at this event today. As the previous speakers all showed us, the Antarctic sea ice zone is at a crossroads. They describe between them a number of dramatic changes in both the climate and the ecosystem. many of which with consequences that will bring irreversible change at human timescales, at a scale of human interest, such as the biodiversity loss and severe changes in the physical system, including down to the daily weather. Next slide, please. Because on Earth we are all one, there are no escape rooms. As this figure by Meredith and al. shows, the oceans are all connected with each other, directly or indirectly, and similar for the atmosphere, which envelopes the whole of the globe, regardless of ocean or land masses. So significant changes in any part of the Earth system will be felt globally. Next slide. To better understand the impacts of the changing Antarctic and Southern Ocean, we must gain improved knowledge of processes that relate to, for example, the ice sheet stability as shown here by the arrows, the details of ocean-sea ice interaction, and the influence of extreme weather events on the Southern Ocean and the surface mass balance of the Antarctic continent itself. Next, please. We also need to gain improved knowledge of how those processes act against the backdrop of the global warming to influence the capacity of the Southern Ocean to act as a carbon sink or source, the effects of ocean acidification, and the role of the Southern Ocean on providing ecosystem resilience. Next, please. To achieve these, there are a number of urgent actions the scientific community jointly, with the support of national funders and operators, as well as the international community, need to carry out. And there's an urgent need for those actions. We need to obtain targeted, synchronous, cross-disciplinary observations of the Southern Ocean and longitudinally from the Antarctic continent down to the coast, across the sea ice zone, ocean, and into the lower latitudes. These observations need to be fit to provide us with scope to derive detailed process information. At the same time, those observations need to inform numerical Earth system models of any scope and scale, and also those data need to provide input into data assimilation as well as to inform climatologies. Antarctica in sync is the opportunity for us to grasp now, with a timeline of it to from 27, 28 to 29. We also need to extend those observations for the longer term. Importantly, we need to be more and more active and engaged in a two-way process, from observations to numerical modeling and simulations, and from the simulations to inform our observatories. Next, please. In addition, the upcoming 5th IPY of 2032-33 will provide the opportunity not only to connect back to Antarctica in sync, but also to initiate or iterate on existing long-term observatories. In addition, next slide, we should, as a scientific community, verbalize our request to build an IPY bridge, to have those few years between Antarctica in sync and IPY to get better understanding of effective build and maintenance of long-term observations. Critical to the success of not only Antarctica in sync, IPY, or any such activity are the measurements, are that we take measured actions and international coordination in all our larger scale observing and synthesis studies. To do this, also, we need to agree on a set of basic background variables that need to be obtained, regardless of the scope, the initial scope of any initiative or observing study. We need to agree on forward-thinking observational protocols and adhere to data standards in all our doing, being it obtaining observations or deriving data and sample processing, and we need to be open in sharing our data. Importantly, all this needs to happen against a carbon-aware implementation scale. Next slide, please. Please let me move to the policy implication based on the scientific knowledge derived by our wider community. We need to own the information, and we need to accept that we are at this very time at a threshold. We are well within the so-called critical decade of climate action. Delaying effective measurements will magnify any undesired consequences associated with drastic global warming, be it in the climate sphere or in the ecosystem. There needs to be a global consensus, even in the face of adversity, to enact strong climate and hence environmental action across all spheres of life and all levels of society, legislation, and executive. Next, please. To remind ourselves, any further climate inaction will lead to obtaining and reaching those tipping points triggered at different levels of warming, as shown here in this figure by Armstrong and McKay, which was published in 2022, only 2 years ago. This figure has been annotated, as noted here, to allow for changes of tipping points or tipping elements that were noted in 23, including the collapse of the Antarctic sea ice, summer sea ice, and catastrophic loss of glaciers in the third pole, and changes in the precipitation across the European Alps. So time is not on our side. Next, please. In summary, the Antarctic Southern Ocean system has progressed from one that initially showed increased variability, such as we saw during the so-called Antarctic paradox, where Antarctic sea ice in extent increased over several years against the backdrop of global warming. But the system now is holding tipping point elements and, importantly, the big elephant in the room, the Antarctic ice sheet, which will lead to long-lasting sea level rise, as Robbie pointed out before. What we are talking now are actions that will be affecting the long-term future. There's clear evidence that the anthropogenic drivers are the leading cause to triggering Antarctic and Southern Ocean tipping point elements. And lastly, we are at the very verge of passing multiple thresholds to rapid and most likely irreversible changes, not only in the Southern Ocean, but also globally. Next slide. I hope you stay with me here when I say that climate science introduced a language around carbon emissions. In the wider community, people doing their daily lives rationalize it into the context of events that we saw petering out just recently across the globe with increased fires, bushfires, or floods. However, it has been the political and economical fiscal same that has jeopardized and derailed this process, this communication. And for example, we have the phrase carbon emission being permutated into a carbon economy, serving the politics. As the joint scientific research community, we implore that any big decision-making considers the input, the established facts, peer-reviewed facts from climate and ecosystems change as equal in their decision-making, equal especially to those of economic drivers and short-term thinking. And these decisions in the decision-making process need to be across all levels of governance. Next slide, please. Climate action needs to occur globally and include everyone. Little voices add up. Big voices need to be considered. And we will require a democratic environment to avert undesirable consequences for everyone, even for those who don't have a voice to speak. I remind you, there is no escape room on this planet. With this, I hand back to Steffi.
Thanks a lot, Petra. Thank you. And with that, I just want to ask all panelists come back here to the panel. Take a seat. So I just put up here again now.
Come forward into these chairs. We can
just move forward. Great, thank you. So we don't have to scream too loud. Great. So we just put up here again our overall take-home messages. So we hope that we could show that the Antarctic sea ice is really drastically changing, and that these changes have not only local implications but really global ones, and that it's there's no other way than we to not go beyond 1.5 degrees. And with that, I want to open the floor for questions, which we are like happy to answer, all here on the panel, but also the people online. Are there any questions? If not, so maybe I just I'll like yeah.
Yeah, no, I was just going to ask. So you did mention like Antarctica and things, the International Polar Year. In light of the fact that we don't really understand how Antarctic sea ice is changing, we need a lot of observations. How best can we get these observations, and how can, I guess, countries work together to make sure we're getting the right observations?
Yes. So the question was about how can we best like get observations done in a way that we can tackle exactly these problems that we just mentioned. And maybe I just kind of like take the question for the moment myself and then hand over afterwards to Petra. So I think it's in particular Antarctica InSync and also the upcoming International Polar Year are great examples where we can show that it's in the end not about like single measurements, but it's about the connection of all these single measurements and following similar measurement protocols so that all the data that we gather in the end are kind of comparable to each other. And this is exactly what these programs and initiatives like aim for, that we do invite like all countries, not only the ones who have like icebreakers, who have the research facilities, but also all the other countries around kind of to really have a really huge international impact in a way that we send scientists from all of different places, but then also like spread our knowledge back into the different nations. And at the same point, it's like key to really coordinate all these science in a way that we, as I said, would just like follow similar observational protocols in all different regions around Antarctica and all different seasons, to then have really like the connection to all of them to get a global but also like full seasonal picture. Petra, do you want to add on that?
Yeah, I think the important thing is to open it up to everyone, as Steffi said, but also to always maximize the opportunity. So I put in underway observations. We need to have an agreed standard set of underway observations that are very low impact on ship time in any staff. So automation of routines is really important, and have to have them rolled out across many assets, across many icebreakers, regardless of who owns them. We also really need to talk between cross disciplines. We take a lot of us take ice cores, sea ice cores, and the way we harvest them, the way we analyze them can actually be maximized, so that not too many people put the effort that is replicating not much new news. So we need to spread that. And then it really is about hitting on a basic fundamental set of minimum required variables across all the disciplines that we should deliver on all those voyages across InSync. And, sending people and instrumentation across different assets is really important. So thank you.
Yeah.
Can I just add something about InSync and IPY? I think they're like big studies of the polar environment, but they're also stories that we can tell to funding agencies and the public about what we're doing. So a lot of attention gets paid to IPY in terms of like, how are we going to measure this all year round in all these different places? But some of the biggest impacts of previous IPYs have come from like the establishment of Apex and the establishment of various initiatives, organizations, and also just getting more money for cooperation. So not money for science, but money for different agencies to work together. So I think it's a study, but also a story of importance.
Any other questions?
I have a question.
Yes.
Talk about the financial lot here at the COP29. What's the funding gap needed for science?
So the question is for the online participants, so what is actually the funding gap that we are facing here in relation to polar science and all these different initiatives?
Depends what country you're from.
I started that.
Why don't you go first, Petra?
Okay, sorry. Yeah, look, in science, we are really in a money poor environment, and we have learned over the last decades to make do a lot, as much as we can, with very little fiscal resources. But I think it would be for something like an initiative globally of Antarctica InSync, it should be, going to the $1 billion, US dollars at least, and even bigger for IPY InSync. is Antarctic Southern Ocean centric. IPY will talking both poles and the third pole and the high mountain regions. So there's a lot of integration and a lot of more societal touch points. So the budget would have to upscale at least tenfold, and that's on top of the existing budget allocations that we expect. Thank you.
And maybe I could add that the national delegates should also within the nation they should make clear that we need polar programs. Very often, science funds are dedicated to very diverse issues, and polar research is only limited to a very few countries. And having a dedicated calls for polar research would make things so much easier. So people should try to advocate for that, I would say.
Thank you. So maybe one last question to Will in particular. So what would be like the wish list, like from the modeling perspective? So what would be needed in order to decrease our model uncertainties and to get a better understanding of what is happening currently and also the future?
Thanks, Steffi. Well, I think we've already covered on a lot of those issues, and it's having observations and time. So the observations, I think it's really important that we, for the modeling community, what's really important is long-term sustained monitoring, as well as those kind of field campaigns, one-off field campaigns are incredibly important for getting at processes. But if you really want to understand change, we have to track it in real time. And realistically, we don't have enough icebreakers to do that. So we need to use autonomous systems. That's just a logistical reality. The other thing I think is time. Building models and running them is time consuming, and there are some structural issues. It's not just a question of funding, because a lot of researchers spend their time not doing research because funding issues, structural funding issues mean they're doing other things, management. So it's not just a polar issue. They're the same issues that every other academic or every other researcher faces.
All right. Thank you. Is there another question in the room? If not, I want to thank again all panelists. I want to thank the Cryosphere Pavilion to make this event here happen, and I hope that we could convince you all that it's really not an option to go beyond 1.5 degrees in order to save not only the polar regions, but also the impact on the global scale. And with that, thank you, and yeah, enjoy the rest of the talk.
Bye. Thanks, Steffi and everyone.